we're going to dive deep into something that's, well, it's pretty mind-blowing, to be honest. We're talking quantum computing.
Oh, yeah, this is a big one.
It is, it is. Specifically, we're looking at some articles about this new development coming out of China. Have you heard of the Zuchongzhi-3 processor?
I have, and let me tell you, it's making some serious waves in the quantum computing world.
It really is. I mean, remember a few years back when Google claimed to have achieved quantum supremacy?
Oh, absolutely. That was a huge deal at the time.
It was, but the Zuchongzhi-3, it kind of blows that out of the water.
It really puts things into perspective, how fast this field is moving.
It does. So maybe we should take a step back for a second. For anyone who's not super familiar with quantum computing, can you give us the super simplified rundown of what makes it so different and so powerful?
Sure, so think of it this way. A regular computer, the kind we use every day, it uses bits, right? Which are like tiny switches that are either on or off, representing ones and nays.
Right.
But quantum computers, they use these things called qubits. And a qubit, it can be on, off, or both at the same time. It's like a coin that can be heads, tails, or spinning in the air, undecided.
Whoa, okay. That's where things start to get a little trippy for me.
Yeah, it gets pretty wild. And this both at the same time thing, it's based on the principles of quantum mechanics, which is a whole other rabbit hole we could go down. But basically, it allows for these incredible possibilities that just aren't possible with classical computers.
So if a regular computer is like trying to solve a maze by going down one path at a time,
Exactly.
a quantum computer is like checking every path simultaneously.
Exactly. It's like having a million hands all like different routes at the same time.
Yeah.
And that's what gives quantum computers this crazy speed advantage for certain types of problems.
So for something like, I don't know, designing a new drug, which could take years and years with a normal computer, a quantum computer could potentially do it in a fraction of the time.
Absolutely. And that's where this Zuchongzhi-3 really shines. It's been developed by this team at the University of Science and Technology of China, and it uses 105 qubits, which is a huge number.
Big jump, yeah.
And they've got this incredibly intricate system of couplers to connect all these qubits together. It's really a marvel of engineering.
And it's not just a little bit faster, right? We're talking orders of magnitude faster than even the most powerful supercomputers we have today.
Well, yeah, we're talking like 10 times faster. It's mind-boggling.
That's not even comprehensible. It's like Google's Sycamore processor, which was groundbreaking in its own right.
Right.
Looks like a snail compared to this thing.
It really does. But it's not just about the speed, right? It's about what that speed enables us to do. Imagine being able to design a new material with specific properties or simulating complex chemical reactions, things that would take classical computers years or even decades. This processor could potentially do it in days or even hours.
That's where things get really exciting. Like, the practical applications of this are potentially huge.
Huge is an understatement. We're talking about revolutionizing entire industries, from medicine to material science to who knows what else.
It's almost hard to wrap your head around. But, okay, so we know it's fast. But how do we know it's accurate? Like, these quantum states, they're notoriously fragile, right?
They are. And that's a key challenge in quantum computing.
Mm-hmm.
But that's where something called coherence time comes in.
Okay, coherence time, what's that?
So coherence time is basically a measure of how long these qubits can stay in that special both at the same time state, the one that gives them their power, before they sort of collapse back into a normal bit. And Zuchongzhi-3 boasts a coherence time of 72 microseconds, which might not sound like a lot.
It doesn't sound like a lot, no.
But in the quantum world, it's a huge deal.
Really?
Yeah. It means that this processor can do much more complex calculations than anything we've seen before, because it can hold on to that quantum information for longer. And on top of that, you need something called quantum gate fidelity.
Okay, quantum gate. Break that down for me.
Sure, think of it this way. When you tell a qubit to do something, like flip its state or interact with another qubit, that's called a gate. And the fidelity is basically how accurately it performs that gate. Like, if you ask a qubit to do a backflip, does it land it perfectly or does it stumble?
Gotcha. So high fidelity means high accuracy.
Exactly. And Zuchongzhi-3 achieves some really impressive fidelity rates for both single and two qubit gates, which means that it can perform those operations with a really high level of precision. And that's crucial if you want to get reliable results from your calculations.
So it's not just speed, it's speed plus accuracy. That's pretty remarkable.
It's a game changer, really.
So how do you even test something like this? Like, what kind of challenge do you give a quantum computer to see what it can do?
Well, in this case, they use something called random circuit sampling.
Random circuit sampling. What's that?
It's basically like you've got this circuit with a bunch of qubits, and you apply a whole series of random operations to them. And the goal is to measure the output. It's kind of like trying to predict the exact arrangement of a deck of cards after you shuffle it a million times.
Okay, that sounds complicated.
Oh, it is. It's a really complex problem. And it's something that would take a classical supercomputer an insane amount of time to solve. But Zuchongzhi-3, it completed this task in a time frame that's, well, it's 100 times faster than what a classical computer could theoretically achieve.
That's bananas.
A whole different ball game.
It really is. So this isn't just about beating Google at their own game. It's about demonstrating a level of performance that really opens up a whole world of possibilities.
Absolutely. And speaking of possibilities, we haven't even touched on the architecture of Zuchongzhi-3 yet, how it's actually designed. So yeah, Zuchongzhi-3 uses this really interesting architecture, a 2D grid layout for its qubits.
A grid. Okay, I'm picturing like a checkerboard. Is that close?
Yeah, that's a good way to visualize it. Basically, all those qubits are arranged in this 2D grid. And this layout, it has a couple of really important advantages. First, it allows for really efficient connections between the qubits, so they can communicate and interact with each other really well.
No, just so like a city grid helps everything flow smoothly.
Exactly. And the second advantage is scalability. With this grid design, it's a lot easier to add more qubits in the future to make the processor even more powerful. It's like you could just keep expanding the city, adding more and more buildings.
So it's future-proof. That's smart. But I have a question. We've talked about how these qubits are super delicate, right? Like the slightest disturbance can throw them off.
Right, they're very sensitive.
So how do they keep everything running smoothly with all these delicate qubits?
Well, that's where quantum error correction comes in. It's a whole field of research dedicated to protecting these qubits from errors and making sure the calculations are reliable. And the team behind Zuchongzhi-3, they're using something called a distance 7 surface code.
Okay, distance 7 surface code. I'm going to be honest, that sounds like something straight out of Star Trek.
It does sound a bit sci-fi, but basically it's a way of spreading the quantum information across multiple qubits, so even if one qubit gets messed up, you don't lose the whole calculation. It's like having backups upon backups.
So it's like a safety net for those delicate qubits.
Exactly. It's a really clever technique, and it makes Zuchongzhi-3 much more reliable than previous quantum computers. And the fact that they can achieve this level of error correction with so many qubits is really a breakthrough.
So it's not just speed, it's not just accuracy, it's also about reliability. That's a pretty impressive package.
It really is. And when you combine those three things, that's when things start to get really interesting, because that's when you can start thinking about tackling some truly groundbreaking problems.
Right, like you mentioned earlier, things like designing new materials or simulating complex chemical reactions.
Exactly. And remember we were talking about Google's claim of quantum supremacy. Well, there was some debate about whether they truly achieved it, because some researchers later found ways to optimize classical algorithms to perform those same tasks much faster.
So it was more of a specific task kind of supremacy.
Right, but Zuchongzhi-3, it's different. It's not just about performing one specific task really fast. It's about demonstrating this overall level of performance and complexity that goes way beyond what we've seen before. It's like Google built a super fast calculator, but China built a whole quantum computer.
Okay, that's a good analogy. So Zuchongzhi-3, it's not just a one-trick pony.
Not at all. It's incredibly versatile. It can do all sorts of things, and that's what makes it so exciting. It's
Right.
not just about breaking records. It's about opening up this whole new world of possibilities.
Speaking of new possibilities, there's one area we haven't even talked about yet, and it's something that always blows my mind when it comes to quantum mechanics. Quantum entanglement.
Entanglement. Now that's where things get really weird.
It's like the ultimate spooky action at a distance, right?
It is. It is. And it's one of the most mind-boggling phenomena in quantum mechanics. And guess what? Zuchongzhi-3, it can handle entanglement like a champ.
So entanglement, you said things get really weird.
Yeah, it's hard to explain without getting into the weeds of quantum mechanics.
Just
But
try me. I'm ready for the weeds.
okay, well, imagine you have two particles, like two tiny marbles, and they're linked together in this special way so that whatever happens to one instantly affects the other, no matter how far apart they are.
So if one marble spins clockwise, the other spins counterclockwise automatically, even if they're on opposite sides of the planet.
Exactly. It's like they have this invisible connection, and it's instantaneous. There's no time delay.
That's just, I mean, that's crazy. How is that even possible?
I know, it's mind-boggling. And it's one of the biggest mysteries of quantum mechanics. But the thing is, it's been experimentally proven time and time again. It's real, even though it seems impossible.
Okay, so what does that have to do with quantum computing and Zuchongzhi-3?
Well, entanglement is actually a key ingredient for a lot of the most exciting applications of quantum computing. Like, for example, super secure communication.
How so?
Because with entangled particles, you can send information instantly and unhackably. It's like if someone tries to eavesdrop on the communication, they immediately break the entanglement, and you know someone's trying to listen in.
Wow, so it's like the ultimate encryption.
Exactly. And there's even more far-out stuff like quantum teleportation, where you can potentially transfer the state of one particle to another instantly across vast distances. It sounds like science fiction,
It does.
but it's something scientists are actually working on right now.
Okay, I think my brain is officially melting. So we've got this insanely powerful processor that can solve complex problems faster than anything we've ever seen before.
Yeah.
And on top of that, it can tap into this mind-bending phenomenon of quantum entanglement, which could revolutionize everything from communication to, well, maybe even teleportation someday. I mean, what's next? What are the next big steps in quantum computing?
That's the exciting thing. We're really just scratching the surface. There's still so much we don't know, and there's still some big challenges to overcome.
Like what?
Well, one of the big ones is scalability. Like, how do we build quantum computers with even more qubits, thousands or even millions of them? And how do we make them even more stable and reliable so they can operate for longer periods of time without errors? Those are some of the big hurdles we need to overcome.
So there's still a lot of work to do, but the progress that's being made is incredible.
It is, and it's happening at an amazing pace.
Yeah.
Like, just a few years ago, this level of performance would have been unimaginable. And now, here we are, talking about a 105-qubit processor that can harness the power of entanglement. It's a whole new era for computing.
It makes you wonder what the world will look like in, say, 20 years when this technology really matures. Will we all have quantum computers on our desks?
Who knows? It's hard to predict, but it's fun to speculate, right? Maybe we'll have quantum smartphones that can solve complex problems in the blink of an eye, or quantum simulations that can help us design new life-saving drugs or materials with incredible properties.
Or maybe we'll be teleporting ourselves across the globe for our morning commute.
Hey, anything's possible, right? That's the beauty of it. We're just at the beginning of this journey, and who knows where it will lead.
It's pretty inspiring, to be honest. So as we wrap up this deep dive into Zuchongzhi-3 and the world of quantum computing, I'm left with a sense of awe and a whole lot of questions.
That's a good thing. Keep those questions coming, because those are the questions that will drive progress in this field.
And to all our deep divers out there, if you're not already fascinated by quantum computing, I highly recommend checking it out. It's a mind-bending, fascinating, and potentially world-changing field. And who knows, maybe one of you will be the one to make the next big breakthrough. Until next time, keep exploring and stay curious.